Car collision avoidance radars are supposed to work as far as 100 metres, but Andrew Anderson and other experimenters decided to push the limits of the technology to see just how far they could reach with some clever engineering. Using simple machined antenna parts and satellite dishes, they've already reached more than 60 kilometres. This is another episode in my race to reach the maximum possible range, limited by the absorption of oxygen and water vapour in the atmosphere, and machining parts for a system that can achieve record-breaking distances. For the next step, I needed to make 1 or 2 of the special mmWave combiner cavities. No, 3. OK, 4. 7? A dozen. Baker's dozen? OK, 20. Oh, good grief. I got carried away again, didn't I? Better make some feedhorns too. Right, you lot, clear off. Starting from Andrew's design, I added a feature that allows much finer control of the cavity combiner that fits above the chips made by SiliconRadar, and allows experimenters to try out a wide range of interchangeable antenna types in the quest for maximum distance. Andrew's great idea was to use a pair of the chips, each with its own custom antenna, and found he could pass signals over vastly greater distances than when they're used properly in a vehicle radar, using the feeble reflected signal from a target. There are huge engineering challenges in trying to couple the signals into and out of the chips with high efficiency, and then finding ways to extend the range by a factor of several thousand. But that's where the real fun starts. We're using sophisticated data encoding techniques to send and receive signals that are way too weak to be heard, but can be detected by signal processing software from deep under the random thermal radio noise. The biggest barrier is the atmosphere itself. 122 GHz is right on the edge of one of the strong oxygen absorption lines, and water vapour is also a very strong absorber. Reaching record-breaking distances is going to need great mechanical engineering, very clever software-defined radios, cutting-edge decoding programs, and a lot of careful planning around humidity and temperature levels. First though, I need to make the intricate precision parts to help squeeze maximum possible performance from the SiliconRadar chips. This is a piece of 5/8 inch CZ121 brass bar, which will work fine to make the coupler bodies, which are a little less than 15mm diameter. OK, 16mm is close enough. I'm ambidextrous with measurement frameworks. I'm from that generation born late enough in the 1950s to have to learn imperial CGS and SI units, although we called them MKS for a while. Small things are measured in angstroms, then nanometers, micrometers, thou, millimeters, inches, feet, meters, then miles. We needed a lot of different rulers. A quick sanity check with the posh micrometer and it looks like we're on target. So a finish pass and we'd be ready to drill out the central hole to 3.8mm for reaming later.
Camera wobble detected. Hopeless operator error. Installing Amy. Please wait.
Installing Amy, your favorite artificial intelligence machining expert's engineering system. I'm snarky and never make mistakes. Unlike Neil. Hee hee.
Just what I needed. I like to spin drills as I insert them into chucks in some sort of vain hope that any chip stuck to the jaws will magically avoid being nipped and causing a tool offset. It's an entirely irrational belief, but it gives me a nice warm feeling that I'm somehow controlling systematic errors. Sad, isn't it? I'm using the drill to remove any burr around the hole so I can slip a 3mm gauge block between the face of the workpiece and the tip of the drill. Then I set the tailstock DRO to 0 so I can drill the 7.5mm tapping hole to a precise depth. Before anyone squeals in anguish about how I should be cast into a pit of brimstone for metrological abuse, this is a cheap Chinese gauge block from eBay. It's remarkably precisely ground to within a micrometre using my MAR millimess on the big granite surface plate, but for my purposes it's a consumable. It's appalling really, considering the amount of work that's been put into making these damn things and shipping them halfway across the world. These split point cobalt stub drills are marvellous. In steel I often see 4 spiral chips, wide ones from the main edges, but then 2 tiny ones from the chisel overlap of the relief grinds. These ones are machine made, but decades ago my father taught me how to do that grind. I'm terrible at it. In his later years he was a tool and cutter grinder. My main role was being a disappointment. A light chamfer of the tapping hole helps to make the thread entry nice and smooth. Doing it after tapping really munges up these 0.5mm pitch threads. The next feature to add is the M8 by 0.5mm fine pitch thread for the barrel. I'm using a 4-flute high-speed steel hand tap but popping it in the tailstock chuck so I get perfect alignment. I'll finish the last few turns by hand. Despite expert advice suggesting that lube on brass is for simps, I use a splash of WD-40 when I'm cutting lots of these threads. I don't know if the last few threads have a less than perfect finish from the creaking and yelling that the tap makes, but a slosh of WD keeps it quiet. I try not to use it when filming. It's hard to find a suitable solvent to clean it off successfully from lenses and filters and cases without dissolving something. Warning to headphone users and those of a sensitive disposition, there's a bit of squeaking ahead. Next features the 7mm diameter shoulder, which acts as the end stop for the threaded horn core. It's a critical element as it prevents the core from destroying the chip if it's screwed in too far. Once more I'm using the 3mm gauge block to set the reference position of the tool. The horn core's got a 3.98mm spigot which runs in a 4mm reamed hole in the coupler. Next step's to drill a 4.3mm relief at the start of that hole to make assembly easier. This 4mm reamer's a fairly fancy one that came from Cutwell. They were having a promotion and I can't resist a bargain. Anyway, it's been totally fab. Etymological note. I'm from the 1960s, so I'm permitted to use the word fab unironically. Normally I use a bit of lube with a reamer, but not when I'm filming. I don't want to get any more oil on this dreadful camera. Now the bore's reamed, that's the last of the internal features complete. So I'll cut the outside to the finished diameter and cut the step. This is a high rake polished carbide insert for aluminium with a 0.8mm tip radius. It makes a really good finish on brass, he said with ominous foreboding.
Neil, that finish looks absolutely terrible. I bet you've been rough and careless with that insert again. Naughty boy.
Oh dear, she's right. As usual. Time to turn that insert around. I always knock the tip off or use a dot of paint when I rotate an insert so I don't reuse it later by accident. I've got history for that sort of mistake. Look, I know the insert position should be totally repeatable, right? I'm just paranoid in case I knocked something. Anyway, it's another excuse to use my marvellous Mitutoyo micrometer micrometer. Try saying that after a few Bacardis.
Hey, it really isn't hard. Me, too. Toy. Oh, not toy you.
A nice sharp insert doesn't spray brass like that blunt one did. Nice curls and chips. Now the barrel's at 14.85mm diameter, I need to turn the front section to 11mm to give a bit of clearance so the nut can be tightened with fingers. That shoulder's also useful when paired with a mounting clamp that's got a split collar reamed to size. The end of the threaded section needs a light chamfer. This next stage uses high precision metrology requiring a shim made from processed cellulose coated with a china clay glaze. OK, printer paper to you, madam. I set the tool so the paper's just trapped, leaving a thou or two. That's a 50th of a barleycorn for those listeners in the colonies. I'm not quite sure why I chose a 45-degree chamfer for that shoulder, but now I've made several quarter bushels of these things, it just looks right. In related news, it just happens to be the same angle as my chamfer tool. Spooky that. Eyeball technology is plenty good enough to line up the outer edge of this parting tool with the end of the part. I've set the 0 on the y-axis DRO and moved in by a very precise 18 and a bit millimeters, so let's part it off. Okay, that looks alright. As I still haven't bought any right biased parting inserts, I'll nip the remaining ring off with my parallel jawed pliers off camera, 'cause I'm too lazy to use my phone camera. Also, I'd have to hold the phone in my teeth or something. Must get another tripod. As if I need anything else to trip over. One day I'll get a proper camera and lighting rail installed. One day.
Did anyone notice how Neil forgot to clean the chips off the taper? He certainly didn't. Hopeless.
This little mandrel's got an M8 by 0.5 thread and a machined face to fit the end of the coupler body so I can cut it to length. If I was clever, I'd have made it the same size as the couplers so I could use the same collet. If I was clever. If by some miracle you're still with me at this point, I would be hugely encouraged if you could poke the like button, just as though I was a proper YouTuber. First step's to touch off the tool against the shoulder and zero the DRO.
Neil, that plaster on your finger is really attractive. Can't you blur it out in post or something?
2 words. Slicing carrots. I'll take off the excess length in 2 cuts. The chip on the circuit board that this coupler fits over is just less than 1 millimetre tall and 5 millimetres square, but with solder pads, so an 8 millimetre diameter cavity is needed for the chip. The signal cavity is formed from the end of the 4 millimetre reamed bore of the coupler. This 8 millimetre 4-flute end mill has lightly radius corners, but sharp corners would also be fine.
A likely story. He picked up the wrong mill. Such a fool.
I'm using a 3-cornered scraper to take a very light deburr of the edge of the cavity. That deburr of the outer edge is important to avoid damage to the solder resist on the printed circuit board, but has to be narrow enough to avoid the mounting holes. When I polish the body, I'll turn that into more of a radius than a chamfer using a fine file. Great, that's another coupler done, apart from drilling and tapping the M2 mounting holes and giving it a polish. Only another 23 to go in this batch, so here we go again in 3, 2, 1. I made the spacer pin thingy from a scrap of Delrin to stop the coupler from falling down the collet bore and getting stuck in the innards of the vise. Ask me how I know this can happen. I've centred the collet chuck using a dial test indicator fixed to the spindle, but as the critical dimensions are all relative to the 4mm reamed bore, I use a 3.98mm pin machined on a bit of brass rod to check the exact alignment for the bolt circle. Well, weenie screw circle then, except it's a square. When I used the recommended 1.60mm tap size drills, the squeaking of the tiny M2 taps was awful to behold. It sounded like they were on the verge of snapping, so now I'm using 1.65mm drills and the result is smooth and stress-free tapping, but the threads are still a decent fit on the screws. So let's get the DRO set up for 4 holes starting at 45 degrees, 11.85mm pitch circle diameter, centred on the 4mm bore. I've set a depth stop to make totally sure the holes are only 7mm deep. Force of habit and hard experience means a lot of pecking and chip clearance. It probably isn't necessary in this CZ121 brass, but it's a sort of a muscle memory thing now. Comes from drilling 1,000 small holes in nasty, gummy C101 copper bar. Bad times. Yay! Only 92 more holes to do in this batch. Great. One of us doesn't own a light spring rate tap follower, so has to use a pointy bit of brass. Luckily, because the clock spring on my Bridgeport's broken, it only takes light finger pressure to keep the pointy brass thing in contact. My fabulous Tapmatic thingy's a bit too butch for these little taps. I tried making an adapter collet, but setting the tension was too tricky and I really don't want to risk any snappage. Yes, I hear the howls of protest from the Taps Protection League about abusing spiral flute machine taps using a hand wrench, but there is exactly 0.012% chance of me using straight flute hand series taps. Maybe 0.011% in fact. It ain't happening. 96 drilling ops and 96 tapping ops is enough. Using 3 or even 2 tapping ops means so many that I'll need an extra digit on my abacus to count them. Just no. I realise this deburring op looks mightily awkward, but I'm having to reach around a tripod, camera and 2 lighting rigs without knocking anything. I'm almost ambidextrous, but I can't reach any better with my left hand. Or either of my feet. The new 1.65mm drill is a huge help. The little spiral tap just chews its way right to the bottom of the holes without any complaints or screams of anguish. I'm going to count this as progress. Many thanks to the various commenters on the tiny tap video about drill sizes not always being right in tables found on the internet. My excuse is that the table on page 963 of the Machinery's Handbook only starts at M2.2.
Not wishing to intrude into your reverie, but for Pete's sake, you really should make a proper extraction tool.
There must be an uninstall menu somewhere.
In the next enthralling episode of Machining and Microwaves, threading, boring and math, plus more sciencing than you can shake a stick at. Will Neil delete that annoying AI machinist?
So rude.